Yes, class. Good evening.
Good evening, ma'am.
All right, class. So in modern physics, atoms was completed last Sunday, I guess. So we have to complete nuclei to complete the unit of modern physics. Now see, nuclei is a very, very short lesson. We'll be able to complete it. So let's start with it. See, there are only two topics that you have to study in this. I'll tell you. Firstly, class, just understand. Few basic topics are there that will just build up your numerical power. Fine. Numerical solving questions, these will just build up. So very, very basic concepts are there. Otherwise, radioactivity portion has been deleted from your syllabus. So that's why we do not have to do this lesson in detail. Now see, the first thing that you should understand is some terms which includes like nucleons. We say protons and neutrons collectively together. So protons and neutrons are collectively together referred as nucleons. All right, collectively we say it is the nucleons. Nucleons means protons plus neutrons. Now atomic number means the number of protons. So it is represented by Z. And this is not this is actually a universal symbol. In the sense that in any book you take it out, in chemistry book, in physics book, in your NCERT, anywhere, atomic number will be represented by Z only. Yes, we have just started, Usman. So atomic number is Z, number of protons. And mass number means mass of the total number of nucleons. Mass number means total number of nucleons. So nucleons means protons and neutrons. So mass number will be number of protons plus number of neutrons. Fine. Nucleons means proton plus neutrons together. Atomic number means number of protons. Mass number means number of proton and neutrons. So protons, in conclusion, we can say protons are represented by Z. Whatever will be number of protons will be the number of electrons here. And number of nucleons that we have is A, right? Proton plus neutron. So see class, one thing. If proton plus neutron is equal to A, then number of neutrons will be A minus number of protons, and number of protons are Z. So we always write number of neutrons as A minus Z. Now, what all things are very important for you? This one and this one. Both of it will be used in the upcoming portions. Now, four basic terms also you should know. Nobody is going to ask you these terms in the exam. What is the meaning of atomic number? What is the mass number here? No. Four important terms, which includes isotones, isobars, isotopes, and isotones. Fine, these four terms. So what is meant by isotopes? Isotope means same proton number you have, but different mass number. So how do we represent a chemical? When you write a chemical symbol, be it for any element, sodium, potassium, helium, nitrogen, calcium, chlorine, argon, any symbol, you write the chemical symbol. On the lower left corner of it, you write the proton number, Z, atomic number, which is present. Fine, whatever it's the atomic number. How to remember the atomic number? Just the number it has in the periodic table. Like helium has the second place, first is hydrogen, then it is helium, so helium is 2. If you calculate from the starting, you will see calcium is arising at the 20th position. So calcium's atomic number is 20. So our entire periodic table. From there, you can remember this value of Z. Now, apart from this, A is the mass number, which is written on the top right-hand corner. So when this lower portion is same, you have this exact value. But mass number is getting different. If you have same atomic number, it means it is actually the same element. Like take the example of hydrogen. You must have heard of the 3 isotopes of hydrogen which are present: protium, deuterium, tritium. So all these have the same mass number. All of these have the same atomic number. That is the atomic number of hydrogen, 1, 1, 1 each, all the 3 will have. But what makes them different is in the mass number. Protium has 1, deuterium has 2, tritium has 3, like this. So such elements are known as isotopes. Various isotopes exist, like isotopes of chlorine are also there. Many radioactive elements are also present. Fine. So no need to go into radioactivity details, just a brief introduction. Then isobars are opposite. You have the upper portion same, that is mass number is same, but here in the denominator you can see, not denominator, in the corner, lower corner, you can see the different values of atomic number, like chlorine and sulfur. Both have the mass number around 37. Chlorine also has 35, but we are taking the isotope 37. Isotope having mass number 37. So chlorine has 17th value in the periodic table, sulfur has 16th. So both are differing in their atomic number, but mass number is same. Likewise for calcium and argon. Calcium is 20th element, argon is 18th, but both are having the mass number as 40. So these are isobars, same atomic number, but same mass number, but different atomic number. Then you have isotones. Isotones means same number of neutrons. So before starting with this, remember I made you write A minus Z. A minus Z means the difference between this top part and bottommost part for both the elements should be same. Like 37 chlorine if we take, because chlorine also has mass number 35. Mostly we use 35 only for the calculations. This is isotope 37 I've taken. And potassium 39 and 19. So if you subtract 37 and 17, you get 20. But when you subtract 39 and 19, you're still getting 20. It means both these elements are isotones. Because none of it is same. Mass number is also not same. Atomic number is also different, but the difference is same. So these elements are isotones. And isomers you must have heard of. Mass number and protonic, the atomic number, they are not concerned with that. They have different energy states, as in their structures. Different optical isomers are there, geometrical isomers are there, different types of elements isomers are there. Different states, different energy states, right? Different configuration. They can differ in structure, differ in branching, differ in the functional element. So that is completely part of chemistry. We will not discuss it over here, but this was just the introductory part. So from here, nothing is going to come as such in the exam. Note down this part, but it will be used further when we study. Note it down, then we'll see something which is related to this list. Okay, now see the next thing you have to remember, that is the atomic masses. So AMU, the atomic mass unit, this is present of some elements, electron, proton, neutron. So do not look at this hydrogen part. Just look at this electron, proton, and neutron. Class, this value, one thing remember, in nuclei, you do not have to round it off. If you round off the values in nuclei, your marks will be deducted. Precise exact values are required here. But do not worry, the calculations which involve are just simple addition, subtraction. So do not worry about the end digit values, but do not round it off. So electrons, protons, and neutrons mass can be required by you in any of the questions. So it's better if you remember these three values. Right, it may be provided to you in any of the questions, but it's better if you directly remember it. At least these three values for electron, proton, and neutron. So value of mass of electron is 0.0055 AMU. Mass of proton is 1.0073 AMU. Mass of neutron is 1.0086. Fine, these three values you should remember. Now these will be useful when we'll be doing mass defects. First, before we come to mass defect, two important topics are actually there. Nuclear density is there, and one is nuclear size. Class, remember one thing. See, regarding nuclear size, volume of the nucleus, this is directly proportional to mass number. A was the mass number which we studied. So volume of the nucleus means, let's say it's a sphere, nuclei are taken to be almost spheres. So 4/3 pi r cube is directly proportional to A. Forget all the constants. What 4/3 pi will be the constant? What term is left? R cube is directly proportional to A. R cube is directly proportional to the mass number. So if you take roots on both the side, R will be directly proportional to A to the power 1/3. Now see class, we have to remove the proportionality sign. R cube is directly proportional to A. So we could say R was directly proportional to A to the power 1/3. But what is the constant that comes? So R naught is just a constant that we put this R naught value here, which I have put it here. This R naught. This is just a constant term whose value is 1.2 Fermi meter. Class C, 1 Fermi meter is 10 to the power minus 15 meters. The way you have one conversion of centimeters into meters, 1 centimeter, we write it as 10 to the power minus 2 meters. Like the same thing, 1 Fermi meter is 10 to the power minus 15 meter. So because somewhere in the questions, you will get the questions where you have to leave your answer in terms of Fermi meter, sometimes in meter. So it's better if you remember this conversion. So value of this constant is 1.2 Fermi meters. That is 1.2 into 10 to the power minus 15 meters. So R is radius of the nuclei. I'll write it down. This R is the radius of nuclei. And A is the mass number. A is the mass number, and R naught is this constant. So this value, this formula, this is used. Very easy questions come from this part. I'll tell you what type of questions come, but before that, one more thing, nuclear density. This was the size, not the density. What is the general formula of density? Anyone? Normal, general formula of density from your chemistry, physics.
By volume.
Hmm?
Mass by volume.
Mass by volume. Perfect. So this is mass by volume. So here also, if we are taking the nuclear density, we'll put it as mass of nucleus by volume of nucleus. So mass of nucleus, we have assumed a mass that is small m. This mass we have assumed. This is, let's say, average mass of nuclei. Now, why have we taken average mass? Because nucleus can be different. Different elements will have different nuclei. So we have taken an average as m. So what will be mass number? M is the number of nuclei that are present. So we'll multiply it by A to get the entire mass number. So mass of nucleus will be small m into A. A is the mass number. M is average value of mass of a single nucleon. Right? And volume of nucleus will be, see, volume will be what? 4/3 pi r cube. This will be just the volume. But we know r cube is equal to r naught cube into a. Right, r was equal to r naught to the power a by 3, a to the power 1 by 3. So that you can write r cube as r naught cube multiplied by a. Same thing I have written here. This is actually value of r cube, 4 by 3 pi r cube. So this is 4 by 3 pi r cube. From here, see the a, this in the numerator cancels this in the denominator, right? Both the mass number gets cancelled. So this shows you that nuclear density is independent of mass number. Now see class, 3 is a constant, average mass of a nucleon is a constant, 4 is constant, pi is constant, even R naught is constant. R naught's value is also constant, no, 1.2 fermimeters. That is also constant. So if we put all the values, we should get one specific value, because now it is not depending on elements atomic number or mass number. You could see it directly clearly, no? Here, when you saw it, A, both the A's got cancelled, mass number is getting cancelled. So when you put in the values 3 into mass of the proton which you have, because nucleus mass we are writing, 4 into pi into r naught cube. R naught was 1 fermimeter. So we put the value of r naught as 1 fermimeter only. You will get a proper value, that is 2.3 into 10 to the power 17 kg per meter cube. So this is not depending on anything. No constant, no variable term is coming here. All the terms are just constant. A specific value of nuclear density you have. It means even if I replace calcium's nuclei by argon's nuclei, other elements of the physical quantity will change. But the nuclear density, it will still be 2.3 into 10 to the power 7 kg per meter cube for any nucleus. Why? Because you can directly see this is not depending on any atomic number or mass number, that it will be specific. Had it been depending, then we would have taken what? We would have taken that element's mass number. We would have taken that element's atomic number. But you can directly see no element is involved here. This is just a complete single value. So it means nuclear density is independent of mass number and atomic number, both, obviously both. So for all the elements, this is a very constant value, 2.3 into 10 to the power 17. See, this comes class, this both the things that we have performing, the formula based question comes from the above part, nuclear size, and nuclear density questions also. How the questions come, I'll discuss 2 to 3 questions with you. First, note down this portion. From here, then I'll discuss some questions with you, because questions do come from this part, especially from nuclear size. Nuclei Z. Last lesson of modern physics. Written till here, class.
Done, ma'am.
Yes, ma'am, done.
Like this class. Very easy questions you will get because the toughest part was radioactivity. So that is not a part of your syllabus, so do not worry about it. Calculate radius of germanium to the power 70. So this means something is written on the top. How do we represent a chemical? This is mass number definitely, because had it been the atomic number, it would have given in the bottommost left corner. So this is how you represent a chemical symbol also. So germanium is given as 70. That is mass number is 70 and R naught. See class, this I wanted to tell you. R naught's value when it is specified in the question, use that value. Then do not use 1.2 fermimeters. It will give you 1.2, 1.25, 1.3, 1.1 only. But if R naught's value is not provided, then directly without giving a thought, use 1.2 fermimeters. Like right now 1.1 is mentioned, so that is fine. Now see, how do we write R? Radius we have to find out. Radius is R naught multiplied by mass numbers cube root. So this will be R naught is given 1.1. I'm not converting fermi meters, just so that we'll get the final answer also in fermimeters, 1.1. And then this is 71 by 3. So see, 4, around 4. Because if you see the cube of 4 is around 64. No, so it will be 4.12 around. Should be around 4.12. So when you take out the values, you will get this as 1.1 into 4.12 something. 4.53. So 4.53 ml will be after multiplying it by 1.1, no? So yes, right, 4.53 per millimeters is the value of radius. Good, correct. Right, so like this, you will have to find out the radius. Weightage is also not much. Now, second question says express 16 milligram mass into equivalent energy. So we didn't do anything right now, which includes energy. But see class, your equation, which had no, the Einstein's theory of relativity equation, E is equal to mc square. If the questions come, see, we have done this equation when we did dual nature of radiation and matter. That time also we did. Even in atoms also we discussed when we are doing de Broglie wavelength. That time also we discussed. But actually the question that will be coming, question will be the same, but the weightage will be given to nuclei lesson. So E is equal to mc square from there. So mass is 16 milligrams. Let's convert 16 kgs. C squared, that will be 3 into 10 to the power 8 meter per second whole square. This will give you how much? See, this will 3 into 3, that will become 9. And 9 multiplied by 16 will be 144. So 144 you have, and 16. 16 is the power. So 13, 10 to the power 13. This much of joules will be the answer. Note down these two questions, then I'll discuss some more questions. So 2 topics are only there. One is this, that includes nuclear size and density. Other one is mass effect. Yes, class. See, this question says, assuming protons and neutrons have equal masses, calculate how much times nuclear matter is denser than water. Means you have to compare the density of nucleus and density of water. So density of nucleus value will still be 2.3 into 10 to the power 17 kg per meter cube. And what is the density of water, class, in SI unit? SI unit of water. 1000, yes, it's actually 997. So we take it as 1000 kg per meter cube. 1 gram per ml in CGS, and in SI unit, we write it as 1000. So 1000 kg per meter cube. Some of these values, no class, you have to remember by yourself. Question does not provide. So to compare the density, let's take the ratio density of nucleus by density of water. This will be 2.3 into 10 to the power 17. This I'll write it as 10 to the power 3. So 2.3 into 10 to the power 14. This will be the no unit because units will get cancelled. So this much denser is nucleus from water. One last question to be discussed. Note down this question and send me, as soon as you complete writing till here, send me the solution for the fourth one as well. All of you in the chat column while writing, send me the solution of fourth one. Fourth one is the easiest question of all the questions that we have discussed right now. All of you should try at least fourth one after writing the third. Ahmed, correct. Others also, apart from Ahmed, Asta, Alan, all those who are there in the class, Anushka, Ima, try at least the fourth one. 2 more minutes, then I'll discuss. Yes, yes, Imad. Good. Correct answer. C class, if you don't have to even calculate in such questions. You didn't have to calculate here also. What did I say? It is independent of mass number. Whatever element you say, it will remain. Yes, Jiva, 2.3 into 10 to the power 17 kg per meter cube. Density of nucleus, see, that will remain fixed. Density of nuclei, that will remain fixed. It will be 2.3 into 10 to the power 17 kg per meter cube. This value will remain fixed. Fine. Quickly note it down, then we'll start with this topic, mass defect. Just note down this value, all those who didn't. Now see, mass defect means what? Mass defect has a formula, a very big formula it has, but see, I'll tell you how to write this formula. Mass defect is, see, total number of protons. Total number of protons that are present is Z. Fine. Mass of a single proton is MP. So total mass of proton will become ZMP. Just go by unitary method, one liner. Mass of a single proton is MP. And total number of protons, that is atomic number, total number of protons, initially of the class, only in the initial segment of class, we had seen that it is Z. So total mass of protons will become ZMP. Now, number of neutrons, remember I told you A minus Z. So number of neutrons is A minus Z. Mass of a single neutron is Mn. So total mass of neutrons will become A minus Z into Mn. Fine. So total mass of protons ZMP, total mass of neutrons A minus Z into Mn. So when you add both of these, total mass of nucleons, that is mass of protons plus neutrons, it will be sum of ZMP and A minus ZMN. That is what has been written here and here. Now mass defect means total mass of nucleus is something. When you subtract the mass of nucleon from this, whatever is the mass that is left, that is known as mass defect. So you subtract the mass of nucleus. Mass of nucleus can be anything. It will be mentioned to you in the exam. In the question, it will be mentioned to you. So here we have taken Mn. So subtract Mn from the sum of the nucleons. I am again repeating. Mass of single proton is MP. Total number of protons are Z. So total mass becomes ZMP. Total mass of protons. Similarly, total mass of neutrons, it will be A minus Z into Mn, because A minus Z is the number of neutrons, Mn is the neutrons number. So sum of ZMP and A minus ZMn will give you minus Mn. So this quantity that you obtain is mass defect. But more importantly than mass defect, why are we so focusing on this mass defect is to understand the concept of binding energy. See, binding energy means if I have this nucleus and I break its component, let's say protons and neutrons, I have separated all the components. So this energy that is required to break all the constituent elements of the neutron into its individual components, this is known as binding energy. And this binding, see, everything is written to you, written in the notes that I've sent you on WhatsApp, everything is written in detail over there as well. So do not worry about the writing part. That's why pay attention here to understand and learn, and then you can refer to the notes. So this is binding energy. Now binding energy formula is also there. The formula of binding energy is also there. That involves your mass defect. That's why understanding mass defect is better. Now, how to calculate binding energy? Simply first step will be always calculate mass defect. Whatever data is given to you, use that. Whatever data you remember, use it, calculate the mass defect. Fine. Once mass defect has been calculated, multiply it by C square. C, delta M C square. Just similar, E is equal to mc square. So here the energy becomes binding energy, mass becomes the mass defect, and C will still be the speed of light, 3 into 10 to the power 8 meter per second. So E is equal to mc square. Based on this, we have binding energy is equal to delta mc square. So this is delta M, ZMP plus A minus ZMN minus Mn into C square. Now class, one more thing. If I want to get the energy into electron volt units, when we were doing especially modern physics, the initial part, that is dual nature and all, what unit of energy we were using? We were using electron volt. Completely we were dependent on electron volt. This much electron volt energy is there, then multiplying it by h nu and seeing. Last weekend only we had seen all this. So all these, when we saw delta M into C square, it will become a tedious task for us. No, 3 into 10 to the power 8. First you're doing this, then multiplying, squaring it, and then multiplying it by mass defect, then dividing it by 1.6 into 10 to the power 19, and then getting your final answer in electron volt. No. What will you do? Delta M calculate and directly multiply it by 931 mega electron volt. Your answer will be mega electron volt. If you wish, you can convert mega 10 to the by multiplying it by 10 to the power 6. If you wish, you can get it. But maximum answers, you can leave it in mega electron volt. So calculate delta M using the formula that I've told you and multiplied by 931, you get your binding energy. And if by chance binding energy per nucleon is asked, so either by multiplying it by C square or by multiplying it by 931 mega electron volt, any of it, just divide it by the mass number. Just divide it by the mass number. That will give you binding energy per nucleon. For each value of nucleon, you will have the binding energy. Right? So I'm again repeating, we'll see a question on this. This is also an important topic. Mass defect is sum of number of, basically difference between mass of nucleus and total mass of nucleons. So ZMP plus A minus ZMN minus Mn. Then binding energy is required to break up the materials into its constituent elements. So you multiply mass defect into C square or multiplied by 931 mega electron volts to get your binding energy. And if it is binding energy per nucleon, then you will divide it by the mass. Am I clear till here to all of you?
Yes, ma'am.
Yes, ma'am.
Okay, note it down. One numerical we'll practice, then you will see how to solve the questions on this. Question, and one more thing, I'm again repeating for those students who have joined late. Class, for questions from nuclei, do not round it off. I'll show you the question also. Then once you see the question, you will feel that, okay, 1.00867, I can leave it till 1.008. No, write whatever values are given. 8 digit, 5 digit, 6 digit, write the value, solve it, add, subtract properly, because here if you round it off, your marks will be deducted in the final exam. Note it from here, then we'll practice a numerical. Look at this question. It says calculate the binding energy per nucleon of calcium. So atomic mass, atomic number and mass number both are provided, 40 and 20 respectively. Given that, see here in this question, mass of neutron and protons are provided. If it is not given, initially in the class also you have written, you have to learn at least the three values, mass of neutron, proton and electron to be on the safer side. And mass of nucleus is given. Mass of nucleus is this. This is the mass of nucleus. Now, see, ZMP, total mass of protons, ZMP, the total mass of protons. Number of protons that are present are 20. So you will write 20 multiplied by mass of protons. So that will be 1.007825. So I'll not round it off. I'll write it exactly 1.007825. So this will be around 20.1565. So this is ZMP till now. Then A minus Z into Mn. See A minus Z. 40 minus 20. 40 minus 20. This is your A, this is your Z. So A minus Z, this A minus Z will also be 20. So it means again you will write 20. So this will be 20. Then 20 multiplied by 1.008665. So this will be around 20.1733. So this is ZMP and this is your A minus ZMN. So we'll add this around 40 you should get, no? So ZMP plus A minus ZMN would be equal to sum of this 20.1565 plus this is how much? 20.1733, right? So this should be how much? This is 20.1565. So it should be around 40.3298. So now we have to subtract the mass of the nucleus, that is mass of calcium atom. How much it is given? I think answer would be 0.34 something. 39.9625. 39.9625. Something else I think was also there. 2589. A huge value is there. 89. So how much is it? This will be, yes, 0.367. This much is the mass defect. This is just the total mass defect. Now we have to find out first binding energy per nucleon we are calculating. So binding energy will be 0.367 multiplied by 931. Always try to get your answer in mega electron volt until mentioned, because that will make your calculation much easier. Fine class, this will be comparatively much easier. So, and yes, we have to divide it by mass number. So mass number is 40. So 0.8, it will be how much? Into, we have 931, no? So that will be 341.677. When you divide this term by 40, you get 8.54. So all these calculations you have to do by yourself. This much around this will be your answer. Binding energy, that is joules per kg. This is your answer. And all the questions are exactly like this, ditto exactly like this, the questions that have come in your exam that are present also. So just remember this pattern of solving, this method of solving, your work will be done. Note it down. Still any doubts you are having, let me know. Get it clarified right now.
Ma'am,
Yes, Asta.
Ma'am, the mass of neutron, proton, and all will be given right in the exam, like with the question.
See, that's what I was saying. It's not necessary that it will be given, because why I'm saying this, because many previous year questions are there that do not have these values. So to be on a safer side, mass of neutron, proton, and electron. Initially of the class, no, I admit you right in terms of atomic mass unit. Remember these three values to be on the safer side, because if it's not given, even you by knowing also, you must be knowing how to solve the question, but you will not be able to solve it because of lack of the values of all these. So remember it, like in this question, it was given. This I have not added myself. It was given by the question. So in some questions it will be, and in some questions it cannot be, because it is separately given in your textbook. So it's better if you remember it. Plus, see, one binding energy curve is also there, but it's not properly made on the screen over here. So it's better if you, just a second. See, binding energy curve is properly given in the notes which I have given you, and your book also it is given. So this curve, you just have to see the variation of this binding energy with the different mass numbers. This is also incorrect. This should lie here at 56, because you all know the mass number of iron is 56. So don't go by this, just to have a rough idea from this. See, it says that for all the isotopes of hydrogen, protium, deuterium, tritium, all the isotopes, it is directly increasing. Binding energy's value is directly increasing. You can see on y-axis binding energy is there, on the x-axis mass number is there. So value is increasing. All the hydrogen isotopes are present, protium, deuterium, tritium, all those are present. So these are increasing. But when you reach helium, you'll observe a dip is present. Means the mass number is increasing, but binding energy is decreasing with a sharp turn. And again, it is increasing and decreasing. Again, increasing and decreasing. One more element was there. Boron was, I think, here in one of the dips. So you will observe these sharp peaks that are present. This is just done experimentally. All these values are done experimentally. Then again, this will keep on increasing. Maximum value is reached for iron. Iron is 56. Mass number who's 56, and binding energy's maximum value that is obtained is 8.8 mega electron volt. This is the highest value that will be obtained, and then you will notice that all these values are decreasing. Iron had the highest value, 8.8 mega electron volt. Then after this, all the values, see, mass number is still increasing. But from here you can notice it is, here it is something around 7 point something, here it is around 7.9, this is around 6, then it is again, this is around 5 point something, and it is decreasing. So this is how you see the variation of binding energy curve in the periodic table. Fine? Clear to all of you?
Yes, ma'am.
But do not draw this graph. This graph is properly given in the notes which I've shared. So nuclei is clear. This was all about nuclei. No other portion is left in nuclei. This is all that is coming in your exam. The two topics initially that we discussed, nuclear size, nuclear density we discussed. And then we had seen binding energy per nucleon, mass defect, and all these that was included. And finally, at the last, you have binding energy curve. All these are the topics that are included in nuclei. So I'll start with semiconductors. Then we have, I think, half an hour we have, no? Yes, more than half an hour we have. Okay, let's have the introduction part of semiconductors so that we can complete a major portion of it tomorrow. See, semiconductors are not conductors, they are not insulators, they lie in between they have the properties that are in between the conductors and insulators. So conductors have very low value of resistivity and they have high values of conductivity. Whereas if you take the properties of insulators, insulators have very high properties of resistivity and very, very low values of conductivity. That's why we say insulators are poor conductors of electricity. But when you see all the experiment data for semiconductors, semiconductors have the values of resistivity and conductivity in between insulators and conductors. That's why they are not properly conductors, they are not properly insulators. They have the properties in between. If conductor has the highest value of conductivity here and insulator has the highest value of resistivity, right? Semiconductors in both the cases will be in the middle only. For conductors and insulators, you can see some values are different. But for semiconductors, it will be in the middle of it. But the reason we should be using then conductors for all the purposes, or we should be using insulators for some other purposes which will be fulfilling it. The reason is that semiconductors have the ability to control current. How they control the current is not a part of your syllabus. When we used to do transistors and all, we used to see how to control current and calculate the value of the current. That also has been deleted. That also you don't need to do. So just remember that the ability of the excessive use of semiconductors because of its ability to control the current. Now, this is one basis based on resistivity and conductivity. One more basis is there, that is band theory. So band theory, I'll discuss it. First, copy this page, then I'll tell it. Yes, Amada, I'll resend it. Or you do one thing, just text me personally on WhatsApp. I'll share you on your number as well. MHC, the topics that have been deleted from semiconductors include logic gates that has been deleted. Rectifiers are there. You have Zener diode deleted. All the Special purpose diodes, photodiodes, solar cell, these are also deleted. Then transistors are also deleted. So you just have this part, types of semiconductors, and then you have PN junction. That's it. Rectifiers are also there in brief. So quickly note down everyone, text me done, then I'll start with energy band gap theory. See, bands are what? Bands are closely spaced energy levels. These are known as bands. So there are various bands that in which electrons are present having different levels of energy. So two types of band you have to understand. These one, no, that have the free electrons available, these are known as conduction band. Actually, these are all the electrons that contribute in the electricity part, conductivity part. So all the electrons that contribute in conduction or conductivity part, these are known as conduction band. This band, energy band, is known as conduction band. Various energy levels are there. Now, the band in which electrons are present, but these electrons do not contribute to current because they are bounded. They are in bound state. So these are valence band. So two bands, conduction band and valence band. Difference between these conduction band and valence band, the energy gap that is there, these are energy bands. No, conduction band has energy, valence band also has the amount of levels of energy. Difference between these bands, this is known as the energy gap. And based on this energy gap, based on the conduction band, valence band, also we can classify semiconductors, conductors and insulators. We can distinguish between the three. See, if like this levels are present, so this will be the very least lowest level of conduction band, right? And these are the different levels. So this will be the highest level of the valence band. So we usually write it as EC and EV. So EC will represent lowest level energy of conduction band, while EV will represent what? It will represent highest energy level of valence band. So conduction band and valence band. This is just the basic. Plus, anyway, if you're not able to understand, please stop me right there. Ask me in the chat also, you can ask, or unmute, you can unmute yourself and also ask. Now see how to differentiate it. Firstly, let's talk about conductors. See, in conductors, the conduction band is partly filled with electrons and the valence band is completely filled with electrons. Now, two setups are possible for conductors. Either it can have a small band gap. Band gap means separation between the conduction and valence band, or it can overlap also. If you see such arrangements, it means you are seeing conductors. So 2 points to be remembered: valence band completely filled and conduction band partly filled, right? These 2 points, as well as you can remember this point also, that it can be overlapped as well. So this is the characteristic of conductors. Now, how to differentiate it between semiconductors and insulators? See, in insulators and semiconductors, both of it, conduction band will be completely empty. Conduction band will be completely empty. No electron will be present, and valence band will be fully filled. This is how you differentiate between conductors and semiconductors, insulators. But C class, conductors will be differentiated because conductors will be having conduction band filled, partly filled, right? But how will we differentiate insulators and semiconductors? Because in semiconductors also valence band is completely filled and conduction band is completely empty. So it means insulator and semiconductors also have to be differentiated. right? So that will be differentiated on the basis of this energy gap. The energy gap is very large. That's why insulators are not able to perform the conduction. We say no, insulators are poor conductors of electricity. Reason is this only because the energy gap is so huge that electrons are unable to jump and reach the conduction band. Energy gap should be this value, you should remember, greater than 3 electron volt. If the energy band is greater than 3 electron volt, this energy gap, then you say it is insulators. If you see the energy gap is less than 3 electron volts, you call it as semiconductors. This is how you differentiate between semiconductors and insulators. Similarity is valence band fully filled, conduction band empty. Difference arises between the energy band gap. Right, suppose here also I had taken the example, energy gap of diamond is given as 6 electron volt. So you know energy gap is 6 electron volt, it is more than 3 electron volt. Definitely that means diamond is an insulator. If you see silicons 1.1 electron volt, less than 3, that means semiconductors. 0.72 electron volt, again less than 3, again a semiconductor. And class silicon and germanium are very two important semiconductors. So it's better if you remember and learn the value of the energy gap of these two semiconductors, because this can be asked to you in the exam just for silicon and germanium. By chance, if it is asked, then you will not be able to, if you will not be able to write it, then it will be very difficult for compensating the marks for semiconductors, because semiconductors and the entire modern physics, these are having good weightages and are easy to score. So try to have a good command on all these lessons. Last year only these portions were coming, but now you have the first book also, term 1, term 2 part is not there here. So you have to keep in mind how to balance, because first book is a little tougher as compared to the second book. So this is how you differentiate conductors, partly filled, insulators, band gap more, and semiconductors, less band gap. This is how you differentiate it. So this is just the differentiation part that you have to remember, distinguishing part, note it down. Then we'll just focus on semiconductors now. Now we'll not include conductors and insulators in our discussion. And any doubts, please ask me. Get it clear right now.
Ma'am, could you scroll up? Yes, ma'am, done.
Just text done once you have written till here. All right, all those who have completed, you all can leave. We'll continue the rest of the part of just semiconductors tomorrow.
Okay,
Yes,
thank you.
ma'am.
I'll just message you,
Ma'am,
ma'am,
can
for
I
the
say?
notes. No?
Yes, Mother, I'll send. Thank you so much.
Thank you.
Thank you, ma'am. Bye, ma'am.